So thermodynamics, entropy, free energy, and reaction direction. This is the unit that we're going to start, that we're going to wrap a lot of things up with. As a matter of fact, a lot of the things we're going to talk about today are things that we talked about already, so it's kind of a review. But you should be familiar with the first law of thermodynamics. We know that in chemistry, to be energy cannot be created or destroyed, so the total energy of the universe has to be constant. The internal energy of a system is the sum of the kinetic plus the potential energy, and changes to energy that occur through changes in heat and or work. So change in energy is actually defined as the sum of heat versus work, or the sum of heat and work. In chemistry, we refer to that as enthalpy. And because change in energy during a reaction or during a process is too difficult to measure at each individual step, we are only really concerned with the amount of energy that was present at the beginning versus the amount of energy that was present at the end. So we only talk about the change in enthalpy. Questions about that? Moving on. Reviews of ways to calculate change in enthalpy of a reaction. So we can use the delta H formation values to calculate the change in energy of a reaction. That is, delta H formation values always describe the formation of 1 mole of a compound from its elements. So for example, the delta H formation, or the enthalpy of formation of ICl, would be half I2 plus half Cl2 to give us ICl. The change in enthalpy formation for an element in its standard elemental state always is 0 kilojoules per mole. So I2 would be 0 kilojoules per mole. Sodium by itself would be 0 kilojoules per mole in terms of its change of enthalpy state. And then we can also use the change in enthalpy formation values to get the change in the enthalpy of the reaction. So and as you may forget, it's the sum of the products minus the sum of the reactants, where M and N are coefficients from the balanced chemical equation. And we did this a bunch earlier this year, so this is kind of a review. Any questions about this? Move forward. We can also calculate the change in enthalpy of a reaction by using Hess's law, in which case we can manipulate a reaction going in one direction to help to eventually get us the actual reaction that we're looking for. So in this case, I have methane decomposing into carbon and hydrogen, and carbon and oxygen making carbon dioxide, and hydrogen and oxygen making water, which gives me the combustion reaction of methane plus oxygen makes carbon dioxide and water. And as a result of that, the sum of the enthalpy of formation reactions for these particular 3 steps is the total enthalpy of the actual reaction. And we've done that before. Yes, sir?
And if like you flip it, it's like 1 over 294?
It's inverse. So so it'd be negative or positive. Okay. Anything else? We can also calculate the change in enthalpy of a reaction by using bond energies, and this actually is an example of a sample problem that we did when we did this once upon a time a long time ago during first semester. So we have to remember that the energy needed to break chemical bonds, and energy is released when chemical bonds are made. So the change in enthalpy of the reaction is equal to the energy of the bonds broken plus the energy released when the bonds form. So an example over here has the fact that we are going to take chloroethane and chlorine and make dichloroethane and hydrochloric acid. So the change in the bonds that are being broken plus the change in the bonds that are being formed gives us the total change in enthalpy of this particular reaction. Does that seem vaguely familiar? Okay. We can also use a calorimeter and collect data to help us calculate the change in enthalpy of a reaction. We would use the formula that says Q is equal to mass times specific heat times delta T. And that particular formula gives us the ability to understand that idea that energy is released during a reaction is the same as the energy being absorbed by the materials in the calorimeter. And also, energy being absorbed by the system is the same as the energy being released by the materials in the calorimeter. So energy goes out, energy comes back in. It always has to be equal to one another in one way, shape, or form. Has to be kept track of, rather. Questions about that? We also talked about exothermic and endothermic reactions, and to sort of review that, if temperature increases, that would give us a positive change in temperature, since the temperature of the surrounding is being measured. Since the bonds in the products are more stable than the bonds in the reactants, the chemical potential energy of the system is lowered. The extra chemical potential energy is converted to thermal energy, so the outside temperature increases. So temperature goes up because it requires, because energy is given off. Does that make sense? And then in this case, the temperature decreases. We have a negative delta T since the temperature of the surroundings is being measured. The bonds of the reactants are more stable than the bonds of the products. The chemical potential energy of the system increases because thermal energy from the outside is converted into chemical potential energy, so the outside temperature goes down. So energy is being added. We okay with that? Okay. In physics, I'm sure you discussed the second law of thermodynamics already. And the second law of thermodynamics centers around entropy. The entropy of the universe is always increasing. That's what the law says. The process proceeds in the direction that increases the entropy of the system and the surroundings is important to understand. It's my understanding that in physics, you guys just talk about entropy as being chaos or chaotic, but you don't really assign a value to it, at least in the scope of this class, in the scope of Greendale's physics class. But for chemistry, entropy is designated as S. And it's a measure of the number of ways to arrange particles in a system with no change in internal energy. So what that means, if I have a bucket of Legos, I can potentially build multiple different structures, as long as when I build those multiple different structures, I don't change the energy of the system. Entropy is an extensive property, and it depends on the amount of substance present. So if I have a bucket of Legos and I'm trying to measure entropy versus a semi-truck trailer full of Legos, the semi-truck trailer full of Legos is going to have significantly more entropy than the bucket will. Why? What's wrong with that? Legos is the problem? Oh, yeah. Oh, yeah. Gotcha. Well, I don't know if it triggers as much as Pavlov dog responds. Same. Well, it's not like, it's just like when Pavlov's dog salivated. It's the same reaction.
Here's a bell.
Anywho, every way that it's possible to arrange particles in a system is called the microstate of that particular arrangement. The more complex the molecule or the system, the larger number of microstates can be made. So, for example, ethane at 298 K has more microstates than methane at 298 K because ethane is a more complex molecule. More atoms, more vibrational and rotational states, more microstates. Whereas methane at 298 Kelvin has more microstates than methane at 273 Kelvin. More energy in the system, more motion of the particles, more microstates. Okay? And since we're talking about laws of thermodynamics, we might as well talk about the third law as long as we're here. The third law of thermodynamics says the entropy of a perfect crystal at absolute zero has to equal zero. Well, I don't think we need to worry about a perfect crystal. If we just say an energy of a crystal at absolute zero has to have an entropy of zero. That's what this is saying. So there's a formula for it, where entropy is equal to K times the natural log of W, where K is Boltzmann constant, and W is the number of possible microstates. You don't have to memorize the Boltzmann constant. It is actually not given to you on the back of the AP exam, which would indicate that the College Board does not believe that this is something you're going to actually have to calculate. Therefore, you should understand, though, how this works. So if there is one possible microstate, the natural log of 1 would be 0, and 0 times anything is 0, so that means that the entropy of that particular system, or of that particular system, is 0. So because of the way that entropy is defined, every substance and or system has some measurable entropy. Now, this next statement is trying to get at the idea that entropy and enthalpy are not the same. So enthalpy, remember, is the change in energy, whereas entropy is the number of microstates that are potentially possible, okay? So in this case, if we say that the change in energy or the enthalpy is 0, we can still have entropy. So for each of the 3 elements listed below, cadmium, calcium, and bromium, I'm telling you that the entropy is 0. But each of those particular elements have a very specific entropy. Now, it would hopefully make a little bit of sense that the more complex the substance, the more entropy it's going to have, which is kind of what's identified here. Calcium is less complex than cadmium, and both of those are less complex than the bromine gas, so they all have there's increasing states of entropy. Now, one thing that we should be aware of, when you see S with that little circle raised to it, to right here, this little guy right here, okay? That little guy right there refers to the fact that we are in standard state conditions, and standard state conditions are defined as 298 Kelvin, 1 atmosphere of pressure for gases, and 1 molar concentration for solutions. So you'll note up above right here, I have change in enthalpy formation in its standard state. So I'm making the assumption that we are 298 K, 1 atm pressure for a gas, and 1 molar concentration for solution. So anytime you see that little circle, that's telling you that you are at standard state conditions. From what I can tell, it appears that the AP College Board pretty much just deals in standard state. Okay, so be aware of that. But if you take the chemistry in college, chances are you're going to be dealing in things that are not always in standard state. So that's why I'm making this distinction. Questions about that? Here's a visual representation of what I'm trying to get at here. So as the complexity of the molecule increases, we get more entropy. So in this particular case, I have nitrogen monoxide, I have nitrogen dioxide, and I have dinitrogen tetroxide. As I add more and more atoms to the structure, I get more and more complex, and the more and more complex gives me more and more chances for microstates. The more microstates means more entropy. So far, so good. Yes?
So like, how are we supposed to know which elements are more complex when we just like see elements?
Bullet point 2 here says entropy of elements follows the pattern. Elements that are more complex have more entropy. So hydrogen versus aluminum versus xenon, okay? Most entropy, least entropy.
What if they're all in the same group?
Well, as you go down a group, what happens to the elements in terms of complexity? They become more complex. So as you go down, you would be able to reason if they're in the same group, they would become more. They'd have more entropy as you go down.
Whatever has the most electrons.
Same period going from left to right. You would also be able to reason that it gets more complex going from left to right.
more electrons.
Well,
Bigger.
what I'm saying is more complex, so more complex would be more electrons.
Okay.
So does that make sense? There are entropy increases when things mix together. So mixing provides an increase in entropy because the mixed system has more disorder. So in this example here, I have circle A, which is ethanol, and circle B, I have, which is a bowling alley. No? Anybody?
What?
It's a real scummy bowling alley where I grew up. Anyway, it's called Circle B.
Oh.
Like you only went there if you were a scumball.
What about circle V?
What?
Circle V.
Circle B is water.
I know, circle V.
Oh.
I was making a joke about your. It's fine.
Never been to Circle V before. It would be a high-class bowling establishment. Nothing but the highest quality bowling shoes. Yes, nothing but the highest quality bowling shoes and the highest quality bowling balls. They
I
would.
think bowling shoes are bowling shoes, V.
What?
Didn't you say you've only wasted time like twice this whole year?
So
Like
when you mix things together, in this case, ethanol has some degree of order to it, and water also has some degree of order to it. But when you mix them together, there is this increase in entropy as there is a subtle increase in disorder. So in the case of ethanol, the intermolecular forces that are attracting the ethanol molecules together, and the intermolecular forces that are attracting the water molecules together, when you dump ethanol inside of water, we end up with some motion of the particles being restricted, so there's a small entropy increase. It's not super measurable, but it is an entropy increase nonetheless because we increase in disorder. Does that make sense?
Yeah.
We also have an increase in disorder when you dissolve solids in a solvent. So in this case, we have something that is incredibly ordered. Okay, so, and what I mean by that being incredibly ordered is we have a scenario where we have a lot of positive and negative things following some pattern, and it's going to be dumped into something that is less ordered. So water would be less ordered than the pure solid. But what ends up happening here, and this is really important to understand, is that the salt itself, so in this case our pure solid, becomes more disordered because it dissociated, so entropy increased. Whereas the water actually became more ordered because it orientated itself around the positive and the negative ions that were present. Does that make sense?
Does the overall enthalpy of the system, or not enthalpy, entropy of the system stay the same?
Well, in this case, the issue is that there's more disorder in a solution than there is in the solvent and the solute separately.
Okay,
Does that make sense?
so there.
So a rule of thumb would say that a solution has more disorder than the solute and the solvent that make it up.
Okay.
That'd be a
So
rule.
we won't be able to, like, if you would give us the entropy of a pure solid and pure liquid, we wouldn't be able to figure out the entropy of the solution without, like, some fancy equation.
I would think that this type of a calculation you would not be asked to do. I think that this would be more of a conceptual style question, your multiple choice, the good, clean, family fun part. Yes, sir.
So overall, the solution's entropy increases?
Yes. Solutions have more entropy than the parts that make them up.
But water specifically is entropy?
So water's entropy goes down, but salt, in this case, entropy increases. But the entire system has an increase in entropy.
Okay.
Okay? Hopefully this will make a lot of sense. If I take a solid and change it to a liquid, it has more entropy. If I take that liquid and I make it become a gas, it has more and more entropy. Because we're adding energy, those molecules are overcoming intermolecular forces. The molecules are overcoming intermolecular forces. They're moving around with greater degree of disorder, and so they become more entropic. I think I just made that word up. on. There is a decrease, though, in entropy when a gas tries to dissolve in a liquid, and hopefully this should make some sense. So if I take a gas and I try to dissolve it into a liquid, a gas that already is at high entropy because the particles are moving rapidly and randomly on their own by definition, if I put them in a position where they lose their ability to move randomly and they slow down, their entropy of the gas is going to go down. Okay? Conversely, if I release a gas from a solution or a liquid, there is a change in entropy as well. So in this case, I'm talking about soda. So if I open the bottle of the soda and you get the psh, and the gas is being released and there's some fizzing, what ends up happening is that the carbon dioxide gas is coming out of solution, and as a result of it coming out of solution, there is more disorder for the carbon dioxide. The increase in entropy drives this process, so we would say that particular process is thermodynamically favored. Question about that? Yes, sir.
So if a gas dissolves in a liquid, would the overall entropy decrease?
So the gas is going to dissolve into a liquid. The gas's entropy is going to decrease, but the liquid's entropy is going to increase.
What if it's like,
What overall for the whole?
I would say the overall, the entropy would decrease.
Yeah.
Okay.
what if it's like a gas that would dissolve into liquid?
What?
So like with the salt dissolving in liquid, it decreased the entropy of the liquid.
Yeah.
Would the same thing happen with the gas?
Well, in this case, the gas is becoming more ordered, but the liquid is becoming less ordered.
Okay.
Does that make sense? So the liquid was doing whatever it wanted.
What if the gas is polar?
Oh, now we're playing the what if game.
Well, because with the salt, it was.
Well, by definition, though, gases aren't polar.
Okay, fair enough.
In general, gases forming from either solids or liquids have an entropy increase. Liquids or solutions forming from solids have an entropy increase, and the number of gas molecules increasing during a chemical reaction would also allow us to expect the entropy to increase. Questions about that? Gonna keep rolling here. Some examples. Predict whether the entropy change in each system is positive and or negative. So in this case, I have a gas mixing with a gas to make a liquid. So we would say the change in entropy is negative because the gas is going to a liquid. What about a solid forming a gas in a gas? The change in entropy or entropy is positive because we have a solid sublimating to a gas. What about a gas and a gas making a gas?
Negative?
Well,
Yeah, negative.
That would be more positive, right? Because there'd be more, so it'd be more, yeah.
well, hang on, hear me out. The number of moles
Well, they're combined, so there's like less different things, but there's the same amount of stuff.
So because the number of moles on both sides of the reaction are equal, okay, we would say that it's actually going to be impossible to predict the sign but if we were pressed to venture a guess, we would say that delta S is close to 0 but we would not say which side it's on. Yes, sir.
So if, for some reason only had 2 on the left and 3 on the right, S would be, wait, yeah, S would be positive, so 3 on the right.
Yeah. Okay. We good? Okay, now, there is some of this thing that we call the homework, but I'm probably not gonna go over the homework until Monday, because you guys have a test on Friday, so
Do we have tomorrow to review in class?
try again.